kind of disagree. I also took formal logic in middle school for some reason. And so that was like all the exact same.
Again, as one does.
I went to a really weird like Catholic school. Yeah, real. But I don't know, like the like when you have to take a word problem and like figure out what to do and like figure out which formulas to use and everything, like that's not as much my thing. Which is also partly why I don't like stats very much.
Yeah. Annalise, can you check the live stream to see that it's working?
Yeah, for sure.
And the audio's good? We're gonna probably start soon.
Only 2 DSA exams.
Yeah, but they're each worth 20%. Wait, can you say something?
Hello? I think it should have been picked up already when I asked you about that.
Oh, wait, okay, never mind. It's working.
Yeah, it's working?
Okay.
All right. All right, we're gonna get started here. If you haven't signed in, make sure to sign in already. So today we're going to be doing ML Monday lecture number 4. We're going to be doing classical machine learning with Scikit-learn. And so let's just get started. Introductions. Once again, I'm Alvin Wong. I'm the education lead of GatorAI. I also have other ML lecturers who will help me throughout the rest of the semester to do some of these lectures here, which is Kartik, Siobhan, and Srinikesh. Unfortunately, they were not able to make it today. So as some of you guys know, this is just a lecture series covering beginner machine learning to intermediate concepts to develop a strong foundational knowledge. And specifically this semester, we're looking at applied knowledge and how to build out these models, right, and actually code them. So for content, all of our slides, all of our lectures will be on our Discord, email, or Instagram. You can go on there and find our link tree, and all of our stuff will be on there. Resources, so the lectures will be released on a Google Drive folder, right? And the videos will always be up on our YouTube channels. All right, so before we go into exactly Scikit-learn and what it is, we're going to be going over a few of the different types of machine learning, just as a brief overview. So some of you guys might remember from our previous semester that there is a lot of different types of machine learning that people like to categorize. So one of the biggest ones is supervised learning. So supervised learning is where you're training a model using a data set of input to label pairs, and all of the data is already labeled for you. So you don't need to worry about anything. You just have to have the data set and then train your model on that data set. And so usually what you are trying to predict is the label, right, for that given input. And this is either regression or classification. So regression is that you are trying to predict a continuous value for that input. So say, for example, if you're trying to predict the price of a house, the price of a house is the label given to a set of input features, right? And so you're trying to predict a continuous value, which is the price. Classification is more like you're given an image of, let's say, apples and bananas, and you're trying to classify, is this an image of either an apple or a banana, right? There's no continuous value, so that would be classification, because you're creating, you're trying to predict labels, right? Or, non-continuous values. There's also unsupervised learning, which is where you have a model and you're trying to train it on a data set that has no labels. So there's no, let's say you have your data set, once again, of apples and bananas, you have no labels to the images. You just have the data set, which are the images, right? And the goal is to find structures or patterns in the data. So normally this is done through clustering, dimensionality reduction, or anomaly detection. So for example, even if you have that data set of apples and bananas, there are certain algorithms that would probably be able to find similarities in images that contain apples versus images that contain bananas. And so it might be able to actually classify that there are two different classes in these types of images if you were to have this hypothetical data set. There's also semi-supervised learning, which is where you train a model using a data set that has a small amount of labeled data, right, and a large amount of unlabeled data. Once again, going back to our example, let's say we have that data set of apple images and banana images. maybe some of that data is labeled, right? So some of the images have already apple labels and banana labels, but a large amount of them don't. Usually what your goal is to try and train a model using that small amount of data set, and you're trying to get your model to be able to extrapolate onto the unlabeled data and actually properly work. So that's an example of some semi-supervised learning. And then finally, there is reinforcement learning. This is where you train a model to interact with like a real-time environment, and you're trying to essentially predict actions or take actions, and you receive rewards based on those actions, and basically the higher the reward is the action that you want to take. And so normally what happens is that you have to manually define a reward function for a model to take in, and then using that reward function, the model can learn to take actions that are in its best interest. Some examples of models that have been using reinforcement learning is, for example, in game bots or autonomous driving, reinforcement learning is used a lot. So we're going to talk a little bit more about regression and classification, right? So these are the main two types of generally machine learning and traditional machine learning models, right? So like we said, regression is a model or a type of model that predicts values from a continuous distribution, right? So once again, going back to that house price example, house prices, if you're trying to predict the price of a house given a set of features of the house, the price of the house is a continuous value, right? And classification is you're predicting a class or a set of features that correspond to the input, right? And is non-continuous is the output, right? And we can see here a list of differences between regression and classification. Most of the times, these are both supervised learning algorithms, right? And so we're already given all of the information to us, and we just need to predict either the class or the value, right, based on the inputs that we give us. And usually how we assess the model for regression is we're using a metric called root mean squared error. And for classification, usually when we're assessing it, we're assessing the percentage of correct classifications, right? And that's how we kind of determine how well our model is doing. So we can see even how we assess the model for regression and classification is quite different in this regard. So today we're going to be going over 5 different models, or what we call like traditional machine learning models that we will implement with Scikit-learn. So I want to go over these models briefly right now so to give you a little bit of a heads up. And then as we go through our notebook today, we'll also be going into the models as well so that you guys can get a good understanding of what's going on. So the models we're going to be going over today are linear regression, logistic regression, decision trees, k-nearest neighbors, and SVMs. All of these today will be supervised learning models. So we're going to have all the labels already given to us. And so this just kind of shows of what traditionally machine learning has been about is normally you already have all of your data, and then you're training a model to predict based on the labels you give it. Nowadays, there's a lot of unsupervised learning, reinforcement learning, where the data is not as nice to work with. And so we can see kind of how over time the types of models that people use in at the state-of-the-art level have changed, So it used to be a lot of supervised learning. Over time, unsupervised learning, reinforcement learning has become much more used methods of machine learning. So for linear regression, we have methods to establish a linear relationship. And we have a question, actually.
Sorry, for k-nearest neighbor, sorry to skip ahead, but that's
Yeah.
just clustering. Isn't that unsupervised, or you can have supervised clustering as well?
So I think you're mixing up k-means and k-nearest neighbors. So k-means is unsupervised. K-nearest neighbors is a supervised algorithm, yeah.
Okay, and it's supervised clustering, so it just makes clusters out of the labels?
Yeah, exactly. So k-means is the unsupervised version, essentially, where you have to predefine the amount of clusters that you're using. K-nearest neighbors, you're already given the labels. And we can actually go over what makes them different later. Yeah. All right. So linear regression, right, is just regression where we establish a linear relationship between the inputs and the outputs. And usually this is a hyperplane with dimensionality of n-1, where n is the number of features that you have for your model. And we'll see exactly how that works and what the hyperplane looks like. But essentially, you're just producing a linear output, a linear function from your inputs to your output, right? And normally you're predicting one value for your output. Logistic regression is basically where you take linear regression and you conform it into a classification method, essentially. And so essentially you have the linear regression model by itself, and what you do is you apply the sigmoid function on top of the linear regression function, and that essentially gives you values between 0 and 1. And then values that are close to 0, we classify them as class 0, right? And then values that are close to 1, we classify as class 1. And so logistic regression, like base logistic regression, can only classify between two different classes because we have values from 0 to 1, right? But if you want to do multi-class logistic regression, it's usually you're just applying multiple logistic regression functions, and you'll have different ones. So you'll have different functions that take in the inputs, and you'll try and kind of put them on top of each other. Decision trees is a non-parametric model in which you establish, essentially you try and break down all of the data into its different classes. It's a classification method, essentially, and you just try and see if you can separate the data, essentially using lines throughout the features, and you kind of separate them if, for example, if this data point has a value greater than this, for example, for its feature, it'll be classified as this class, otherwise it'll be classified as this class. And it's essentially a chain of if statements, if you can think about it. And that's why it's called a decision tree, because it's essentially a tree of if statements, and you just basically go from the root node down through your if statements, and whenever you end up at the bottom of your if statement, you get your class at the end. And so a lot of people like decision trees because they're non-parametric, which means they don't assume any relationship between the input and the output. For example, linear regression assumes that there is a linear relationship between the inputs and the outputs. Decision trees do not have any assumptions. And additionally, decision trees are very explainable, and they're very transparent because you can actually see the if statements laid out for you, and we'll plot that out actually today. K-nearest neighbors, which we talked about briefly before, is a supervised clustering method to establish distance-based relationships between points. That's a little bit off. I'd say K-nearest neighbors is also a classification method, and essentially what you do is K is the amount of neighbors that you're querying your new data point against, and basically it just takes the most common class. So let's say you have your trained model, right? You have all your data points. Let's say you place another random data point that you don't know the class of, and let's say you're querying 20, so K is equal to 20 here. You would check the 20 nearest points around that new data point that you have given it, and essentially you're just giving that new data point a class which is the most common class out of all 20 points closest to it. And like we said, that's different than K-means. K-means is an unsupervised learning method where you're trying to find the groups actually yourself, and you don't have the label, so it's unsupervised, right? SVM is also a classification method by constructing a hyperplane, and the hyperplane will separate the data based off of the support vectors. And this is also a classification. And so base SVM is also like logistic regression. You can only separate between two classes, and you'll see why in our Jupyter Notebook example. But there are different ways to eventually turn SVM into classification with multi-class. But we'll not go over that today. We'll just go over the base one so you guys can get an understanding of what's actually happening with these models. So, we have some images here just to kind of give you an example and help dive deeper in. So linear regression, right, as an overview, predicts continuous values. It uses a best fit line by calculating the mean squared error, solves regression problems, right, which is what we said of continuous values. Logistical regression uses the sigmoid function, right, to squash the output of a linear regression model into between 0 and 1 values, right? And it solves classification problems. Something that's also important to note here is that usually you have to set a threshold, right? So a very common threshold is like 0.5. If your value for that sigmoid function is greater than 0.5, you're part of class 1. If it's below 0.5, you're a part of class 0, right? So theoretically, you could have a data point that gets like a score of 0.5 exactly, right? And it's very ambiguous technically for the model as to whether or not it's a part of class 1 or class 0. But most of the times that doesn't happen. Most of the times the threshold is very good. And we can see here that it very drastically stretches immediately to 0 and 1. So it's very hard to be within that very narrow range where you're in the middle there. All right. This is a decision tree. So we can talk about how, we talked about how the decision tree is usually very transparent, and we can see exactly what's going. It's essentially just a tree of if statements, right? So let's say you have your animal, right? In this example, you're classifying an animal. you check, does it have feathers? If it has feathers, it's true, you go to the true question, and if it's false, you go to the other question, right? So let's say we have a bird. A bird has feathers, obviously, right? So we go to true. Can the bird also fly? Also true. So maybe we'll classify the bird as a hawk, right? If the bird cannot fly, then it's false. So maybe we'll classify it as a penguin. So we can see here how a decision tree is essentially just a collection of if statements all bundled together in a tree. And essentially it leads you to your answer. And this is why people like it, because it is super transparent. And additionally, you can modify essentially what is the model, because this is the model essentially in itself. You can modify the model after you train it. So for example, if you say has fins, true or false, I can very easily myself add another question here and say, does it have fur or something like that, right? And we can add another question, and we can, design the inputs and the outputs. Normally for most machine learning models, it's very hard to do this because most machine learning models are black box models. And even if they are like a little bit transparent, right, it's hard to modify the internal parameters, right, in such an easy way, such as a decision tree. K nearest neighbors, right, we talked about this too. So here we can see exactly what it's like. P1 would be your unknown data point, right? And we already know all the labels of the other classes, right? So we know all those blue points are a part of class A. We know all those green points are part of class B, and all the red points are part of class C, right? So what we'll do is when we have our new data point, P1, that we're querying for, we essentially check, okay, out of all of its 20 or K closest neighbors, what is the most common class to be a part of that, right? And so in this example, it's kind of ambiguous, right? Even if you're to choose 10 and check the 10 nearest neighbors, we probably wouldn't know exactly what class it was, but the algorithm would be able to figure that out for us, essentially. And that's essentially what would happen. So if you had a data point that was very close to class B, it would probably get classified as class P, depending on K, right? And then we have SVM, right? So SVM, like we said, is defined by the support vectors. And the support vectors are the two closest points in the classes to each other. And essentially what SVM tries to do is it tries to find a line between the support vectors that maximizes the classes on one side of the line versus classes on the other side of the line, right? So we can see here that the SVM model found a linear line, right, that separates the green dots versus the blue dots in a very effective manner, except for one green outlier, right, which is on the top here. And so the line is essentially, that separation line is determined by the support vectors. And so that line eventually determines essentially if something is classified as a part of class A or class B. So now we're going to do our Jupyter Notebook. And so we actually want you guys to, have it up and running while we're also doing it. So click on if you can scan the QR code for the link tree, we actually have the Jupyter Notebook already ready for you guys in our notebooks folder, and you can download it. And you guys should be able to run it yourself if you set up your virtual environment, of course, like we described previously. So we'll wait for you guys to get started with that. And this will be lecture 4.ipymb in .notebooks folder. Just give me a heads up or thumbs up. You're good and set up. And you also have your environment ready. You guys don't remember how to do the environment. We can also do that quickly.
Can you do that quickly?
Yeah, we can do that quickly. All right. So I'm assuming you have Python installed?
Yeah.
All right. So essentially what you're going to do is you're just going to make your virtual environment. So I don't exactly remember the command because I use conda, but you'll essentially just run python-m, right? venv.venv, and then you can activate your virtual environment using this command if you're on Windows, or this command if you're on Linux or Mac OS. All right, so we can actually add this here. Dependency management, create your venv dash python.m, and then actually let's go with this. You can add this every time after. And install the libraries. All right. Windows or Linux/Mac OS. Right. All right, good. You got your environment. Did you run the pip install everything here? You ran pip install everything? All right, and then let me know if you can get your Jupyter notebook running. You just have to then lecture for notebook. All right. Okay. So then you should run Jupyter Notebook once you've installed everything on your virtual environment, right? And then it will essentially it'll give you a link called to localhost 8888, right? You just click that, and you should be able to see this here, and you can have lecture for .ip1ib. Oh, or maybe is this the right one? I think it should be the same. Yeah, it's the same. Right. And then you also need to create your kernel as well. Right. Are you ready? Yeah. Are you good?
I'm just installing stuff, so don't look for me.
Okay. Okay, we'll get started. So, like we said, we're going to implement linear regression, logistic regression, decision trees, k-nearest neighbors, and support vector machines, right? And so we should definitely have the dependency management set up in every single, so I'll make sure to have that next time. You're also supposed to have your kernel. I'm going to add this first. Install your libraries, then link your Jupyter kernel to your virtual environment, which I believe is path. All right. So usually you'll do python-m ipy kernel --user, and then or .venv think this is it, to link your virtual environment to your Jupyter kernel. If it is not, that might be the command for conda instead of Python venv, but I'm sure you can search it up. So yeah, essentially what you do is you create your virtual environment, you activate your virtual environment, install your libraries in your virtual environment, then link your Jupyter notebook to your virtual environment using this command, and then you can finally run your Jupyter notebook. Okay. We'll wait a little bit more, a little bit longer. Are you good? Yeah. All right. Okay. All right. So here we're going to have all of the libraries that we're going to use for this, right? And we're just going to import them all. And as no surprise, we're going to be using NumPy, Pandas, Matplotlib, and as we described in our previous lecture slide last week. So we'll check the versions of it, and we'll just essentially see that what versions we're running, so that way you guys can also be aware of that. All right. So we'll start with linear regression. So linear regression, right, is a supervised learning algorithm to use to predict a continuous numeric value by fitting a linear relationship between the input features and the target, right? The data set we're going to be using for this implementation of linear regression is the diabetes data set. And all of these data sets are, they're public on Scikit-learn's data set directory, and so we can just load them in very quickly, right? So we're gonna only use the BMI feature. That way we can visualize the regression line on a 2D graph much easier. But we'll look at all of the different features that this data set has, right? And so for a reminder, the mathematical form of our linear model, right, is essentially we have our parameters as W1, W2, onwards to Wn, right? And then we have B, which is our bias parameter, right? And we essentially just multiply these with the input values, and we get y hat, which is our regression score, right? And so in general form in linear algebra is just W transpose, right, which is W transpose. W is the vector of our parameters, right? And X is a vector of the data point, right, that we're giving it. So y hat will be a single value, right? And so how we essentially test our model, right, or not test it, how we determine the error of it, or what our loss function is to be defined as, is mean squared error, right? And essentially what this is we're just looking at what our model predicts versus what is the actual value, and then we're squaring that value, and we're just taking the average across all of our data points, and that is the mean squared error. And so how linear regression trains is it's trying to minimize the error, right, provided by this loss function. So the goal is to find the parameters W and B that minimize the loss function, which is the mean squared error. So let's load up our diabetes data set. So we'll load it, and we always want to inspect our data as every single time we have our data set, right? So we're going to load it as frame, and we're going to check the information, right? So we can call .info, .describe, .head on it to exactly see what's going on. So we see that these are the features in our data set: age, sex, BMI, BP, I think that stands for blood pressure. And then there's a bunch of other features that are, I think, like medical terminology things. I'm not very sure exactly what it is, but I remember a while ago. And then we can also see all of the statistics for our features, right? Oh, also something that's important to note is that there's no non-null values, right? So our data set is perfectly valid, right, in this case. But we can see some statistical features, right, or statistical descriptors of our features here, right? And as well, we can get the first 5 rows of our data set, right? And so each of these rows represent a single data point, right? And so we can see that here. So we're going to take just the BMI feature, right? So we're taking one feature, and we're taking the values. And essentially what we're going to do is we're going to do the train test split. So we split our data into purposes for training our model, our linear regression model, and then we want to test our model on unseen data. And the reason we want to test our model on unseen data is because obviously if you're given the data beforehand, you can train to it very well and fit on it, you know? It's like giving the answers to a student before they take the test and then asking them how well they do on the test. Obviously they'll do well because they have the answers before, right? So that's why we give them only some of the data and then we train it. So let's train our model. And here we can see, right, what the line parameters are. The coefficient or the slope of this line is 975. and the intercept is 152, right? And so this, because we're only using a single feature, our hyperplane is going to just essentially be a straight line, right? And so we can actually predict on the data set, get our prediction values, and we can also see exactly what it's going to look like, right? So we can see that the root mean square error is going to be 61 here, and we can see our R squared value, right? So 0.31. It's not super high, obviously, but we can see in the graph that there is a trend. That usually, as BMI increases, right, the diabetes target is going to be going up as well, right? And so we can see this here. And we can actually test with different features. So let's say we don't want to test for BMI. Let's say we want to test for BP, right, which is blood pressure. So we can run all of our code again, and we can see kind of the same trend, right? That as your blood pressure increases, your diabetes target also increases, right? And of course, there's a lot of variance in the data, but it shows that there is a trend, right? And the R squared, I'm sure, is not a great indicator, right, of there being a strong correlation, but we can see in the graph that there is a little bit of a trend. Next, we're going to talk about logistic regression. So this is a classification model. So logistic regression predicts the probability of a class, right, by using the base linear regression model, and then essentially we're going to apply a sigmoid function on top of that to squash the values in between 0 and 1. So the data set we're going to be using is the breast cancer Wisconsin data set, and we're only going to select 2 features for visualization to make it a little bit easier for us. Right, so the mathematical form is similar to linear regression. We take our parameters, W1, W2, all the way to Wn, and B, which is our bias. Once we have that, we're just going to pass it into our sigmoid function here, right? And so this will squash the values to 0 and 1. And then we have our classification rule here. So this is where we set our threshold, right? So after the linear regression output gets passed into the sigmoid value function, or the sigmoid function, I mean, if it's greater than our threshold of 0.1, we're going to say that the class is 1. If it's less than 0.5, we're going to classify it as a class of 0. So the decision boundary in this case is a straight line, and we'll see that here. So we'll load our data set, and we can see here that we have 569 examples, right? So these were all taken from real people, right? And so these are all the features that we have, such as the mean radius, mean texture, perimeter, area, exactly, other stuff. Radius error and stuff like this is additional information. And so we can see all of these features here. We have 29 features, but we're going to use 2 of them. And same thing, we have all of the statistical descriptors, right, of our features, as well as we can take a look at the first 5 rows of our data set to exactly see what's going on. So let's take the mean radius and the mean texture to be our 2 features that we're using, right? So once again, we're going to do our training test split, right, to make sure that we train our model properly and that we can test it and see what could its performance be like in the real world, right, on unseen data. So we're going to fit our model for logistic regression, and we're going to also get the coefficients, right? So like we said before, the coefficients is essentially just for the linear regression model, and then we pass it through the sigmoid function. So these are our coefficients, right? And so we can predict on the test set, and so we will get a classification report. So we can see here that our logistic regression seems to be doing okay. It gets a 90% accuracy on 143 test samples, right? And we can see here that our model seems to be doing a little bit worse on malignant, on malignant breast cancer rather than on benign. But we can see it's still doing quite well. 90% is not bad, we would say. It depends on what is the baseline accuracy that maybe doctors have, right? Because we always want to be comparing to a relative baseline. So we can see here exactly what's happening. So we can see here the decision boundary right here, right, which classifies between malignant and benign. And so we can see, I'm not actually sure which one is which. We need a legend for that. Should add a legend later. But we can see that as the mean radius increases, right, that we're getting more relative to class 1, we'll be heading in class 1's direction. If the mean radius is smaller, we'll be in class 0's direction, right? And so we can see that mean texture doesn't seem to have as much of an impact on the class distribution, but maybe mean radius does, Mean radius has a lot. So this is a good way to visualize it. And once again, we can choose different features, right? So let's see, we can take mean perimeter and mean radius again, because we liked mean radius. So let's train our model again. And we can see here that the decision boundary is a little bit harder to determine, right? We can see that it's very hard. And we can kind of get the same thing once again, where as the mean radius increases, we're heading more towards the purple class, right? And mean texture as well, as mean texture decreases, there is a little bit of a trend to go towards the yellow class, right? So this is how logistic regression makes that decision boundary. It's just a straight line, and whatever is on whichever side of that line is the other class. Next, we have decision trees. Decision trees, like we talked about before, is just a series of if statements, basically, and it checks if a feature is above or below a certain value, and it'll use a bunch of if statements to go through that, right? And the mathematical form is we split using, the data is split using a feature and a threshold, and the threshold is determined by the Gini impurity, which essentially determines how separatable is the data, right? And so based on that, we create our prediction and we create our nodes, right, which separate the data points based on the features and the thresholds that the Gini impurity makes us choose, right? So we're going to use the iris dataset. The iris dataset is a dataset of flowers. Oh, it's not working. There we go. So we'll load our iris dataset, and so we can get the flower features, right? So all we have is sepal length, sepal width, petal length, and petal width as our features. So we have 4 features here, and we can see not as many features as our previous dataset, but that's all right. We do not always need a lot of features, right? So we'll do our splitting, and then we'll train our decision tree classifier to a max depth of 3, which means we only have 3 layers, right, in our decision tree. And essentially what we're going to do is the same thing. We're going to just predict it. And so we're going to look at our classification report, and we can actually plot the tree. So you can see here that our decision tree actually does really, really well. Based on the 3 classes, it has 100% accuracy, precision, and recall based on the 38 test data points that we give it. And so we can look actually at our decision tree, right, and we can plot it out, right? So we can see that if the petal length is less than or equal to 2.45, if it's true, we're going to classify it as a set osa. Yeah, we're going to classify it as a set osa flower. If it's false, then we'll have a bunch more else if statements, right? And so eventually what we get at every single leaf node is essentially a class that determines the class essentially, right? And so that's how we eventually get the classification for every single class here. Now we're going to move on to k nearest neighbors, right? So this is a supervised classification algorithm similar to the one we just did. We're going to use the wine dataset, and the wine dataset is also for classes, and it classifies different kinds of wine. And so how k nearest neighbors essentially works, like we said before, is essentially you just do a distance calculation to the k nearest neighbors for that data point. And essentially it's the majority class among the k neighbors, and you're going to make that prediction as for that data point to be a part of that class, right? And so we're going to load our wine data set, right? Same as before. We can look at all of this stuff and we can see it's non-null, 178 data points. We're going to go through our values, or we're going to choose 2 features, which is the alcohol content and the malic acid content, right? And we're going to scale our features this time. The reason we're going to scale our features this time is because k nearest neighbors is very sensitive to features that are scaled to different amounts, because it's based on distance calculation, right? So if one of the features is very, very large, but one of the other features is very, very small, then those features have varying different, they have a very large difference on the impact it has for the Euclidean distance, right? So that's why we're going to scale all of the features, right? So that way one feature does not have, more importance than another feature, just because the feature has larger magnitudes, right? So we'll split our data, we'll train it on the train. We can see it works well. Look at the parameters. And then we can print our results. And we can see here kind of exactly how it goes. So it's like a Y shape is our decision boundary. So we can see that, it's really hard to get the classes of these wines, right, in this data set. There's green tends towards to be around the top. So that means higher malic acid content tends to usually be green. And as well, it usually has around a 0 alcohol content for scaled, right? So we'll have to we can take a look at that later, what the actual alcohol content is, right? And we can see that class 1 has, relatively less alcohol content compared to class 2 and class 0, and it also has less malic acid content, right? And so we can also imagine if we were to have, 3 features, then this would be in 3 dimensions, right? And so we can, generalize this. Maybe we can't think exactly in 4 dimensions, but we can imagine adding a 4th feature, right? And so our graph would be in 4 dimensions, right? And adding a 5th feature in 5th dimensions, so on and so on, right? So now we'll move on to SVMs, which is also a classification. So we're going to use the iris dataset again. And this time, we're only going to consider 2 classes, because SVM, like we said, only can classify between 2 classes, right? Base SVM by itself. And so we'll have 2 classes and 2 features as well to make it easier to visualize. So the mathematical form for that is essentially the same. It's very similar to linear regression, where we generate a line, and then we calculate the class using the sign based on this line, which is, right, our hyperplane. And so essentially we just try to maximize the margin between the support vectors, right? And so to get the possible margin. So we'll load our iris, like before. We'll take only the petal length and the petal width as our 2 features. We're going to split our data, and we're going to train our SVM, and we're going to use a linear line. You can use a polynomial line, but it does take longer to train and can also overfit. So once we have that, we're going to classify based on that, and we can see here we have, once again, 100% accuracy on our iris data set. So it's able to always determine if a flower is of the sedosa variety or the versicolor variety, right, based on our test data set of 25 examples. So we can plot that out and see what that looks like. So we can see here is very clear why the SVM was able to get 100%, accuracy, right? Is because literally the petal length is all you need to know to even determine, right? We don't even need petal width, right? If the petal length is, I think, like below 2.5 centimeters, then you're of the class Setsosa. If your petal length for this data set is greater than 2.5 centimeters, you're the versicolor flower. So it's very easy to see how this SVM is able to come up, with 100% accuracy. But anyways, I think that's it for today for the traditional machine learning models. Just a few takeaways is that usually these traditional machine learning models, they are a bit more explainable and understandable, which is why we're able to almost graph every single one of these models, properly and kind of see exactly what's going on. For different models like neural networks and other stuff like that, it's very hard, to graph exactly what is going on from the input features to the output features because there are so many. And most of the times when you're looking at graphs that kind of explain them, they're like, simplified versions. And of course, when you're simplifying information, you're losing the information there, right? So the traditional machine learning models are simpler, but they're still very powerful and underrated. Not everything needs neural networks or transformers or any stuff like that. Most of these times, these machine learning models can perform very well and sometimes perform even better than the very complicated and black box models, right? So I think that's all I wanted to talk about today. If you guys have any questions, feel free to ask me. If you guys had troubles getting your virtual environment started, you can also feel free to ask me. But I think that's about it for today. So I'll end the stream here, and thank you very much for your time.